So probably the most important topic. Oh, uh, hold on, I don't know why it's doing that. Okay, sorry about that. Just had a little bug for whatever reason, kept erasing my work. Okay, so week two, right? And we're going to talk about rates and word problems and just like in general some other topics that will show up on the AMC 8. So first to start, I like to use this little problem, which is like, say we have one cow, 1 acre of grass, and we give it one day. And in that one day, it eats all of the grass. And then we say like we have two cows, right? And we give them 1 acre of grass. How many days will it take them to finish that acre of grass? And so the simple idea is that, well, we have twice as many cows eating grass, so this 1 acre of grass is going to go away twice as fast. So it'll only take them half a day, right? And so say we have maybe 4 cows this time. Well, this time we have 4 acres of grass. The idea here is while we have more cows, we have a proportional amount of acres of grass, right? So one cow is gonna eat 1 acre of grass, another cow is gonna eat a different acre of grass, and so on for the 4 cows. And so really, this is just the same as this first idea up here. So it would actually take 4 cows the same one day to eat 4 acres of grass, right? And so the reason I bring up this sort of cows, grass, and days analogy is because this is the heart of rate problems. And so the most important formula you guys should know is distance equals rate times time. Or in some cases, it will be work equals rate times time, right? So I think this is pretty self-explanatory. Distance is how far you've traveled. Rate is your speed, and time is, well, just the amount of time that's gone by, right? And then so the distance, not the distance, the difference for when it's work instead is, say you're like filling up a pool, right? Or you're, I don't know, eating, right? These can all be measured in a sort of quantity and done at a certain rate, a certain speed. And so these are also things that the AMC might ask you to analyze. So not just, physical distance, how far did I travel, but also like how much of this did I do? How much of this has happened? That sort of thing. And so, a good way to remember these formulas, is what I call unit analysis. And so you will probably come across this later, in like high school. But it's really useful for remembering what to multiply, and what to divide. So let's just do a really simple example. Let's say, we have a car going at 60 miles per hour, right, for 2 hours. So I think, it's not too hard to tell, right? Each hour we drive 60 miles. That's the rate. And 2 hours is the t total amount of time that we're driving at this rate, right? So we would multiply these to get our total distance. So you'd get 120 miles, right? And so the way you want to think about this is we have, our units, right? So for units here, we would have 120 miles. And then for time here, right, we would have hours. And then our rate is miles per hour. And whenever we have a per, we want to think of it as division. So like, so it'd be 60 miles over hour, right? And so if it was like meters per second, then it'd be 5 meters over second, right? And the idea here is that it becomes really clear what we want now, because if we multiply this 60 miles per hour, right, by our 2 hours, oops, essentially what we can do is we can cancel out the hours, right? And now all we're left with is 120 and the miles, right? And so this works the other way around, right? Say you want the rate. Say you're given that you drive 120 miles, for 2 hours, right? So then our rate there, well, we want miles over hours. So what we should do is we should take 120 miles and divide it by hours. And so this will give us that 60 miles per hour. So it's just remember, per equals, division. And so going off of unit analysis, another thing you will have to do is literally just this. It won't be necessarily rate, but it might just be like converting from one unit to another. So like, say we have 108 feet, and it might ask you something along the lines of, how many yards is this? Right? And so you might think, okay, well, 3 feet, right, makes 1 yard. And so for every 3 feet I have 1 yard. So in 108, how many threes do I have? Well, in 108, um, there's 36. So this would be 36 yards, right? And so what unit analysis does for us is we can turn this equivalence, right, into, a rate. So so we want to figure out how many yards here, right? And we are given that this is true. We want to turn this into information that we can sort of like multiply or divide, to our advantage. So we would say 3 feet, right, equals 1 yard. So if we divide the 1 yard over, essentially what we have is 3 feet over 1 yard. And vice versa, we could also do, 1 yard over 3 feet. And the important thing here is when we divide over, right, all we're left with is 1, right? So we move the 1 yard over, and essentially we just have 3 feet over 1 yard. Well, that's just going to be 1, right? Because they're equivalent to each other. We're treating everything as variables here. And so why this is important is this is called a unit conversion, right? So now what we do with this unit conversion is we say, okay, we have 108 feet. We can simply multiply it by the unit conversion, right? Because the unit conversion is the same thing as multiplying by 1. It's the same thing as multiplying by 1. So that means no matter which one we use, our output is going to be the same as our input, right? So if we multiply this by 1 yard, right? And you can also think of this as like 1 yard per 3 feet as well. Then this is where we get the 108 divided by 3 equals 36. And so this type of unit conversion is really helpful because it makes it more clear whether you have to divide or multiply, and it gets rid of any confusion there. So like, let's have an example, for example. So say we have a current of electrons at um I don't know, let's say 3 electrons per second, right? How many electrons, oops, how many electrons will pass? So these electrons are sort of just like, flowing through a wire. So they're just like uh moving through. And then say we have like something that counts how many, right? How many of these will pass after 10 days, right? And so now we have a lot of conversions, right? We have electrons per second, seconds to minutes, minutes to hours, and hours to days. So it's in our benefit to try to use unit conversion, right? So that we sort of have this linear multiplication of just a bunch of fractions that we can calculate out really easily. So we should start with 3 electrons per second, right? And then what do we want to multiply that by? Well, we want to go from seconds to hours now, right? So each second is 1/60th of a minute. Did I say hour? I'm sorry if I did. I meant minute. So 60 seconds is 1 minute. So we want to multiply by this unit conversion factor, right? 60 seconds per 1 minute. And now from minutes to hours, well, it's the same conversion factor, right? 60 minutes in each hour. And then for each hour, right, we're going to have 1/24th of a day, right? So 24 hours makes 1 day. And then lastly, right, this last one is not a conversion. We're just saying 10 days passes, right? So this is how this would look. And so if you sort of look at the units, right? Boom, 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 right? Everything cancels out and we're left with electrons, which is exactly what we want, right? We want how many electrons will pass. And so I have not done the math for this, but I believe it should be it should be like this. Um, and I wouldn't worry too much about calculating this out, but I'll just do it for the sake of doing it. 192, so that should go here, right? So 2592, and then 000. So that's how many electrons would pass. Does this make sense, guys? On the AMC, these tend to be pretty early problems, because in the end, you're just like doing computations. Um, but if you know how to do them, you can do them really fast. You can save a lot of time for harder problems at the end. So it's important to at least understand how to streamline it, even if you don't maybe fully understand the unit conversion method. Knowing what to multiply and divide is really important. And so another thing about units, is how they carry in dimensions. So, say we have, right, 3 feet again equals 1 yard, right? Say instead of 1 yard, we had a square yard, a yard squared, right? So what does that mean? Well, it means we have like this sort of box. It's a square, and the dimensions are 1 yard by 1 yard, right? What we have to keep in mind here is that this isn't equal to 3 feet squared, right? This is actually equal to 9. And the reason for that is, if we sort of change this, right? Essentially what we have is along the sides, we have 1 foot, right? 1 foot, 1 foot, right? And then these 3 feet make up 1 yard. And on the same side, it's the exact same thing. So we're going to have 1 foot, 1 foot, and 1 foot, right? And this also makes up 1 yard. And so you guys can see in total, right? Each of these little squares is going to be 1 foot squared, 1 square foot. And in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So essentially, what you have to do when you come across these types of conversions is you have to square everything. So it's 9 feet squared and 1 yard squared. This is also something that they like to ask. And so it's just really good to keep this in mind when you're doing a problem. So like, um, say we have like, I don't know, 100 meters squared, and I asked to convert it to centimeters squared, right? Well, then we know 1 meter is equal to 100 centimeters, right? So So essentially, if we square this, we get 1 meter squared is going to be, oops, that's the wrong place to put the comma, 10,000 centimeters squared, right? And then we multiply by 100. So we have 100 meters squared is going to be 1 million centimeters squared. And so it's just important to keep in mind, you square the entire expression. And this is the same for 3 dimensions. So if you have like 1 cubic yard, right? Well, then 1 yard, 3 feet, you have to cube the whole thing. So this would be, oops, not that. 1 cubic yard would be 27 cubic feet. So yeah, just remember, whenever you're doing between dimensions, so like 2D and 3D, you always want to make sure to square everything, even the number. Okay, let's look at some practice problems. So this one says Steve has a pool and it holds 24,000 gallons of water when it's full. And it says it'll be filled with four hoses. Um, and each supply 2.5 gallons. And it asks, oops, gallons per minute. And it asks, how many hours will it take to fill the pool? So, I'll let you think about that one for a few minutes. There's no TAs today, so just message me if you think you have an answer, and then we'll go over it shortly. Okay, it's been a few minutes, so I will just go over this quickly, right? So, if we're thinking about unit conversions, right, we want to think about what we're given. So, we're going to start with 24,000 gallons, right? And then what we have is we have a rate. So, we're going to multiply by this rate. So essentially what we have is 2.5 gallons over minutes, right? But we don't want gallons, right? In the end, we want minutes or hours. So we're going to multiply by 1 minute per 2.5 gallons, right? And then we also have to account for the fact that we have four hoses and each supply this. So this should actually be 10 gallons per minute for all the hoses, right? And so after this, right, we can see gallons and gallons will cancel out. So this will give us the number of minutes that it takes for it to fill up. But we want hours, right? So we want to do another unit conversion where we have 60 minutes, right, for every 1 hour. And so this is complete, right? At the end, these will cancel out, these will cancel out. So we're just left with hours. And so if you just do the math, 24,000, right, divided by 600, this is going to be 40. So it's 40 hours. Does that make sense? I don't see any questions. So yeah, so we can move on. Okay, here is another problem. Okay, there's a lot of specifics here that don't really matter. So I'm just gonna say Bonnie, right? She's on the road from point A to point B, very generic. And this stretch of road is 50 miles. So she goes from A to B at um or not at averaging 60 miles per hour. And then she goes back from B to A, averaging, sorry, it's a little messy, 40 miles per hour. And then the question asks, across the whole trip, so to and back, what is her average speed? And you would answer this in miles per hour. And so, just a hint, if you remember from last week's lesson about averages, the same applies to this week, except for it's a little different. So, what you want to do is you would take total miles over total time. And this is going to be your average speed. This is the formula for average speed, I should say. Um, so yeah, just in case you need to touch up on that. So this problem is definitely a lot more difficult just because it's an actual rate problem, right? This problem was just unit conversions. This is a little bit more applied, so I'll give you guys a few minutes to think about this one. And same as always, just DM me if you think you have an answer. Okay, it has been a few minutes, so I think I will start explaining this one. Okay, so um oh, so really for any problem that you're trying to solve on the AMC 8, you should be looking for something, right? Whether that's usually that'll be a number, right? But sometimes that'll be ideas or like certain numbers, right? Um, and so here, the numbers we need to find are the total number of miles, right? And the total time, because this over this will give us the average, which is exactly what we want to find. And so breaking down this average speed into, okay, we want this and we want this, is something important to know, right? So total miles, okay, well, total miles is pretty straightforward, right? Bonnie goes from A to B, B to A, it's 50 miles. So 2 times 50 gives us 100 miles, right? And we're already, quote unquote, halfway there. Um, because the time takes a little longer to solve for, but we'll explain that in a second. So the total miles, we got it. It's 100 miles. We're done with that. Now we need the total time. And so the total time is where we have to, apply ourselves a little bit. Um, so from A to B, right, we're going 60 miles per hour, and we travel 50 miles. And then we go back from B to A, but this time we're averaging 40 miles per hour, right? And so averaging really just means we can assume that from A to B, they're just moving at 60 miles per hour the whole way, right? Because that's essentially what average means is across all the different speeds, right? We meet in the middle at 60 miles per hour. So we can kind of just assume that that 60 miles per hour is constant for the whole thing. Um, and so from there, right, how we want to find time, well, distance is equal to, oops, that's not an R, rate times time, right? So our distance traveled is going to be 50, right? So let's say this is from A to B, right? 50 miles. I want to make that clear. And then our rate from A to B, right? Our rate is 60 miles per hour. So using that unit conversion, right? Miles over hours, over 1 hour. Miles per hour. We do the division there. And then we multiply by some time t, and t is what we want to find, right? So what we should do is we should multiply some things over, right? Um, so we get 50 miles, right? And then we flip this fraction. So we get 1 hour over 60 miles, right? And that is just going to leave us with t on the other hand, on the other side. And this will give us 5 over 6, right? No, the miles cancel out. So we're just left with hours equals t. So from A to B, we're going to take 5/6 of an hour, right? Well, that's just one part of the journey, right? So from here to here, it takes us this much time. Now we have to find how long it takes from here to here, right? And then we can add those two numbers together, and that'll give us the total time that we need. So from B to A, right? It's the same exact process, and we just get D equals RT, right? So our distance here is still 50 miles, except for now our rate is 40 miles per 1 hour, right? And then again, we have a t. This is what we're solving for. We move things around. And so we should get 50 miles times 1 hour. over 40 minutes, miles, not minutes. And this will give us t, right? And so this comes out to be 5/4 of an hour equals t, right? And also something to note is we are leaving these two in hours because in the end, we want the speed in miles per hour. So if we were to, translate this into 50 minutes, right? It'd be easier to work with the 50 minutes, but we would have to convert that back to some form of hours later on. And so it's much more direct if we just keep it with hours, right? So now we have the first part is 5/6 of an hour. The second part is 5/4 of an hour. So our total time is 5/6 plus 5/4. So this will give us 20 over 24 and 30 over 24. So this will give us 50 over 24 hours, right? And so now this is our total time, and we can finish out the problem, right? So our average speed, remember, is total miles over total hours. And our total miles, if we look back, is 100, right? Because back and forth, 2 times 50. And then now, with this total amount of hours that we just found, we're just going to put that in the denominator, right? And so this will become 100 and then times 24 over 50, right? And so 50 and 100 leaves a 2. So our final answer is going to be 48 miles per hour. Does this make sense, guys? Yeah, okay. So I still have one more problem. Would you guys rather I go over that problem or you guys go on break and then we continue with the set? Oh, wait, problem. I'm seeing someone say problem. Okay, no one else answered, so let's just go over this next problem too. Okay, this problem says Joe, right? He's on his way to school. So this is his house. And then over here is school, right? He's walking. He's walking to school, and then all of a sudden, exactly halfway between his house and his school, he realized he was late. Um, and so for the rest of the way to school, he went 3 times as fast. And the problem says it took him 6 minutes to walk. So this first half where he doesn't know he's late yet versus this second half where he's running. And so it says, how many minutes does it take Joe? How many minutes does it take for him to walk from home to school? So just how long does it take for the whole journey? So remember, right? His running speed is 3 times as fast. Okay, and this one is not too hard. So I feel like you guys can probably get this one down. But since I want you guys to go on break soon, I'm just gonna go over it really quickly. Because I don't think it's as hard as the other one. This one was definitely pretty hard. But this one, if you sort of conceptually understand what's happening, I think it's not too not too difficult. So the idea here, right, is it takes 6 minutes to walk, right? And we don't know what this distance is, but it doesn't really matter, right? Because when he's running, he's 3 times as fast, right? And so a common issue I saw was, okay, if he's 3 times as fast, then this segment should take 18 minutes, right? But if we sort of just think about it, wait a second, that doesn't make sense, right? 6 minutes walking and then 18 minutes while he's running to run the same distance. It doesn't make sense, right? And so instead of tripling 6 minutes, we should actually multiply it by a third for 2 minutes, right? Because he's 3 times as fast. Um, and so I guess sort of the explanation is distance equals rate times time, right? So if we're keeping distance the same, and we make the rate 3 times as much, well then we have to 1/3 the amount of time it takes in order for these to cancel out, and then we get the same distance, right? Um, so yeah, it would take him 2 minutes to run this length since he's 3 times as fast. And so in total, 6 minutes, 2 minutes, we get 8 minutes as our final answer. Does that make sense? Oh yeah, sorry if that was unclear. So the first half he was walking, and then like the story is halfway he realizes he's late, and so he starts running. Um, so yeah, so the second half he's running, first half he's walking. So yeah, I think you guys, yeah, that's my bad. I guess that was a little unclear, but yeah, first half he's walking, and then the second half he's running. Um, I guess I tried to like indicate that with these like with like three arrows instead. Um, that won't be a problem on the test since I'm sort of transcribing. I'm not like writing word for word, I'm kind of drawing pictures to explain the problem instead. So yeah, I think you guys will be fine on that. Okay, so let's go on break then. We'll have a 10-minute break. Yeah, what time to come back from break? Let's say 7:05. Okay. I will see you guys then for the problem solving session. Okay. So this is 8 times, and we have fly, fly equals bug, where each of these letters is a digit. And so like F is a digit, L is a different digit, Y is a different digit, and etc. So B and B, these two digits are the same, these two are the same, these two are the same. Yeah. And it says find the greatest value of fly, or not find, but let fly be the greatest number that can satisfy this equation. So we want this to be biggest. Um, and it says find FLY. So this three-digit number plus this three-digit number. Okay, and so we didn't have time for this in class. So the idea with any sort of letter representing a digit is you always want to express it in terms of variables. So, like, say you have the two-digit number AB, right? So this could be like 51, for example, right? What you always want to do is you want to write it out. And what I mean by that is, right, technically AB represents 10A plus B, right? Because A is in the tens digit, so we multiply it by 10 and then we add B, right? And so for like ABC, right, this would be 100A now plus 10B plus C, right? Does this make sense? Okay, I don't see any questions, so yeah, this is how you want to express numbers when they tell you, digit by digit what it looks like. Is it translates to these things. And this is a very useful tool in certain problems. And we will talk more about this in number theory because what happens is usually you'll have to equate this to a certain other thing. And you need everything to be integers, and we'll talk about how to solve those later. And so here, right, basically what we have is the same idea. However, one thing to note is that we don't actually need to find um, each digit individually. What we can do to simplify things is say, hey, we have this whole group of numbers here, fly and fly. What if we just say that fly is like A, for example, right? And then bug, right? Let's just say bug is like B, right? And remember, bug could be like 324 and fly is like 126, right? So we're just gonna say it's like A and B because then what we can do, right, is do this, right? So fly really means what we're doing is we're taking fly, we're multiplying by 1,000, and then we're adding fly again. Why is this? Well, if we take 126, for example, right? So 126, right, times 1,000 plus 126, right? What we get is 126, 126. That's because this three zeros at the end of 1,000 gives us that space to sort of just like copy it over, right? So essentially what we're doing here is fly is going to be fly times 1,001, right? Because if you kind of imagine fly times 1, and then we use the distributive property to add 1,001 together, right? And so if we just call fly like A, for example, right? Fly equals A, then essentially fly is 1,001 A. And this is a lot easier to work with than this number over here, right? And so bug is going to be quite literally the exact same process, right? We're going to do bug times 1,000 and then bug times 1,001, etc. And so it's going to come out to the same exact thing, except for instead of A that we have here, we're going to have bug equals B instead, or lowercase b, right? So bug is going to be 1,001B. And so if we take these two ideas and we, come back to our equation, essentially what we have is A times, what do we have? 1,000 or 8, sorry, not A. 8 times 1,001A is going to be equal to 1,001B. And so we can very clearly take out 1,001s from both sides and we get 8A equals B. So what this means now is that A, right, remember, is our three-digit number fly, and B is our three-digit number bug. Really now, all we're trying to find is the largest number fly, such that bug basically doesn't go over 1,000, right? So like fly could be like 100, right? And then bug would be 800 or something like that. But another thing we have to be careful of is, remember, F, L, Y, B, U, G, these numbers all have to be distinct. So 0 and 0 would not work. 0 and 0 would not work, right? And so the idea is if we want it to be as large as possible, okay, well, 8 times 125, right? That's going to give us 1,000. But 1,000 is a four-digit number. So we go down. So we say 8 times 124, right? Where 124 is fly. 8 times 124 is going to give us 992, right? But this isn't our answer either because we repeat digits again, right? We have 9 and 9, and B and U have to be different numbers. So if we go down one more time, 8 times 123, now everything works out. Now this is our largest possible values for fly and bug. 1, 2, 3, and 984. So our final answer is just going to be 123 plus 984, which should get you 1,107. Does this make sense?
Yeah.
Yeah? Okay, great. I think the next problem is 4. Yeah, 4. Um, oh, okay. So, blah, blah, blah talks about World Wide Web, doesn't really matter. Download speeds, okay, 56 kilobytes, kilobits, per second. So that's the speed of downloading things. And then it asks, how many minutes would the download of a 4.2 megabyte song have taken to download? And it tells us the conversion. It tells us 8,000 kilobits is equal to 1 megabyte. Okay, so now this is a prime example of conversion factors, right? So we start with our 4.2 megabytes. I'll just shorten it to MB so that it's easier to write. Um, and so we know, right, for every 8,000 kilobits, we have 1 megabyte. So 8,000 kilobits over 1 megabyte, right? And we convert it to kilobits because here, right, we have this other conversion factor, kilobits per second. So now what we can do is we can say, hey, for every 1 second, we have 56 kilobits, right? And so now we're done, right? Because we just wanted, actually, we are not done. We want the amount of minutes actually, right? So in these problems, be very careful, right? Just like I just did, it's really easy to make mistakes with units, right? So when we calculate this out, it'll give us seconds, but we want minutes. It asks for minutes in the problem. So we have to do one more conversion factor, which is 60 seconds for each 1 minute, right? Okay, and so now this is our finished product, and we just have to evaluate this out. And so how I would go about doing this is, okay, I would say 4.2 is like 42. So you can take out a 7 and it'll become 0.6, right? And then here we have a 56. That's perfect. We take out a 7, we're left with an 8. 8, right? 8 and 8,000. Well, now this becomes 1,000. And then down here we have nothing left. So now it's 0.6 times 1,000 over 60. So we cancel out the 6. So we have 0 0.1, oops, 0.10, same thing, times 1,000 over 10. And we cancel out a 10. Oh, this should be another 0 here. And then this should give us 10 minutes. Does that make sense? Okay, I think next up is problem number 1. Oh, okay. So we have these 3 stretches of land, right? And then 3 speed limits. 5 miles, 5 miles, and 5 miles, right? And so it says one car starts here, another car starts here, and they're driving towards each other. And so they want to ask at what point will they meet, and how far is it from this point over here? So this is A, and this is B. Okay, so the idea here is, right, it's a little confusing because these two cars do not get to the 40-mile-per-hour zone at the same time, right? This car is going faster, so it's actually going to hit the 40-mile-per-hour zone sooner than this side. And so what we want to do is we want to take it sort of like one section at a time. So let's just start by comparing when both of these cars will hit this point, right? So 25 miles per hour, right? Miles per hour. And we have 5 miles. So what we should do is just take 5 miles, and then multiply it by 1 hour per 25 miles, right? So this will give us 1/5 of an hour, um, or if you want, 12 minutes, right? And then so for this other stretch of land, right, it's going to be 20 miles an hour instead. And so we're going to have 5 miles times 1 hour over 20 minutes. And so this is going to give us a quarter of an hour instead, which is 15 minutes. So essentially what's happening is, let's just say this is car A and car B, right? Car A is going to get to this point at 12 minutes. And then 3 minutes later, car B is going to hit this point over here. So essentially what happens is when car B hits this point, car A is already ahead by 3 minutes, right? That's sort of the difference that's happening here. Car B will be right here, and then car A will have gone a little bit into the 40-mile-per-hour zone by exactly 3 minutes, actually. So we can calculate how far they've gone in those 3 minutes, right? So in 3 minutes, if you're traveling at 40 miles per hour, 40, or we should actually do 3 minutes, right? And we want to convert to hours. So this is going to be 60 minutes per 1 hour. And then it's going to be 40 miles per hour per 1 hour, right? So if we set up this little conversion table, um, this will leave us with 2 over 3. And so in the end, it'll be 2 miles. So this distance right here is 2 miles in. So after 15 minutes, car A will be 2 miles in, and car B will just be hitting here, right? So that's the first section of the trip, right? Now we sort of know exactly where these cars are, and they're just like they're going towards each other. And the thing to realize here is this once we have both cars in the same speed zone, right? They're both traveling at the same speed. So if they're going straight towards each other at the same speed, they should meet exactly halfway, right? And so we can use a little bit of geometry to calculate that, right? So this whole length is, it's getting a little cluttered. Let's move this middle section. So it's going to look something like this, right? So car A is here, car B is here, right? Now that they're both in the 40-mile-per-hour zone, they're going to go directly towards each other and meet each other at the midpoint of where they currently are. So the midpoint of where they currently are is going to be right here, right? And so if this is 2 miles, right, that means the rest of this is 3 miles because the whole zone is 5 miles long. And so each of these sections is going to be 3/2 miles, right? So now if we come back to the bigger picture, right? So this section is 2 miles. This section is 3/2 of a mile. And then this, of course, is still 5 miles. So they meet at, what is this? 5 plus 2 plus 3/2. 3/2 also 1.5. And this should get you the answer of 8.5 miles. Oh, how much time? I'm not sure. Um, we still have one more to go over, which is number 10. Number 10 is, I think, should be very quick. Um, if I'm remembering correctly which problem that is. Yeah. So it's about a car. It's not accurate. So at noon, they both say 12, right? But then later that day, um, the guy checks his car and his watch, which is correct, says 12:30, but his car says 12:35. And so it asks, he looks at his car later, even later, and then it says 7 o'clock. And then it asks, what is the actual time? And so here, what you need to realize, right, is we're trying to find a ratio because even though the clock is out of, even though the car clock is out of time, right, it still follows a specific inaccuracy, right? It's going to be off by a certain amount of minutes, and we can predict that because it gains time at a constant rate. So what we can figure out is, okay, the difference between these two is the car clock has gone 35 minutes, right? While the real clock in real world time has only gone 30 minutes. So it's safe to say that the ratio of minutes that passes by is 6 to 7, right? For every 6 minutes that pass in the real world, 7 minutes are added to the car's clock. So if we're at 7 hours past noon, right? That's 420 minutes, right? So that means in the real world, it has passed 360 minutes. And 360 minutes is simply 6 hours. So 12 o'clock, you add 6 hours. The answer is 6 o'clock. Does that make sense? That was a pretty quick problem. So yeah, we're right at 8, which is perfect. I guess if you guys want to see any other problems solved, you can ask, and I can tell you sort of like after class. But yeah, I guess as of now, yeah, I will post answers and problems, homework, the lecture notes, whatnot. I will post that later. Shouldn't be later than tomorrow night. So yeah, I guess besides that, you guys are free to go unless you have questions. Um, yeah,
Thank you.
yeah, no problem. See you guys.
Bye.
Bye.